Hello students, so we are finishing up chapter 13 and this is still structure determination, NMR. We're going to focus on a little bit more complex splitting patterns for the proton NMR, and then we're going to go into more of an analysis of the C13 NMR. You can just take a look here, just what I said. So I just want to start with just the concept of splitting patterns where we've looked at really simple situations where you could develop a doublet, a triplet, a quartet. Sometimes they're more complex if there are more H's or if the surrounding neighboring H's are not equivalent. So in that case, sometimes molecules possess accidentally overlapping signals. So let's take a look at toluene. This is a benzene ring with a methyl group. You have 5 aromatic H's. These are not equivalent. Some of them are, but some of them are not. So you get peaks in the past 7 range, but it's a complex pattern. This is actually really nice to, once you see something like that and you see that regularly, that can represent to you a benzene ring, specifically a phenyl with a single substituent. If you have another substituent here in the 4 position, then you get more symmetry. So when you do have a little bit more complexity, you can kind of use that to your advantage sometimes and just kind of unravel and confirm the identity of a structure or allow for a structure determination. So here's a spectrum, NMR spectrum. You have a doublet here, a little before 10. You have this kind of more complex splitting pattern, which is characteristic of this phenyl ring here. You also have peaks within that, a peak here within the 6 to 7 range. It's blown up here to show there are 4 peaks, but it really isn't quite a quartet, is it? The quartet, we've already analyzed the splitting pattern, has that kind of height ratio of 1 to 3 to 3 to 1. That's not really that, so to me this looks like 2 doublets. If you blow this region up here, it looks like you have another doublet within. So let's analyze this further. The blue vinylic H is this blue guy here. This vinylic H next to the carbon off the benzene ring is within that aromatic region. Let's analyze this using what's called a tree diagram. So if you look at this proton here, focus on carbon 2. This proton here has 2 neighboring H's. So it can be split by this first one that's trans to it. This actually has quite a large coupling constant, but basically that proton on C2 can be first split by the C3H and give you a doublet. Then it could be further split by the C1 and convert each of those signals into doublets. So overall, you get 4 peaks in the end. Again, because those are split by 2 neighboring non-equivalent H's, it's not a true quartet. Or if it would have been 2 actually that were identical, you would have expected a triplet. Okay, let's do a problem where you guys figure out what the tree diagram would look like. We're going to look at 3 bromo, 1 phenyl, 1 propene, shown here. And it shows a complex NMR spectrum in the vinylic region. So you have the vinylic H of the C that couples or is split by the H here off C1 and 2 H's off of C3. So you guys draw a tree diagram and predict what type of, how many numbers of peaks are going to be observed. So if we look at this problem, this proton is going to couple with this trans H, this H that's trans to it. That'll have a large coupling constant of 16. You guys could not predict that. But it'll split that into a doublet, and then it should split each of those signals into a triplet when coupled with these methylene H's here. So what that would look like is this. You have your original signal split by H1 into a doublet, and then each of those doublets split into a triplet. But look at this. Each of these are triplets, so you expect 6, but these are kind of coincidental, so it only looks like 5. So this is not necessarily something you can predict in terms of the 6 looking more like 5, but just be aware that sometimes more complex splitting patterns, they can be just not very simple quintets or septets or quartets, but actually involve splitting by non-equivalent H's. Okay, the uses of NMR spectroscopy, I hope you already are seeing how powerful this is. We can confirm identity of products, we can determine the structure of unknowns, which is huge, especially if you're a chemist. Say you're running reactions and you're not sure what products you're gonna get out. Maybe you get a mixture, you do chromatography, you isolate them, you do NMR spectroscopy. This will help you identify what the major products are. This is key for chemists uncovering regioselectivity. And also we can just take a look here at an example, just in terms of the regioselectivity. Let's say we have this alkene. We do a hydroboration and subsequent oxidation. You guys know that that regioselectivity is going to be anti-Markovnikov, that the boron should go away from the bulkier carbon and you should get this predominantly. But there is a possibility you could get this product as well, the more substituted alcohol. So what's key, we'll go ahead and confirm, we'll see just the different types of spectra to help confirm that. But one other key thing is that sometimes chemists are running new reactions and they may expect a certain product, but they get something else out. So what's really powerful is using all of these spectroscopy tools to identify unknowns, because that is actually how new reactions are discovered. So a lot of graduate students, they're doing projects and they're doing basic research, but then they really identify, oh, just this new product has come up. They explore what the identity of that is. They propose a mechanism for forming that, and then they can actually design reactions to exclusively give those products. That's how new reactions are born. Okay, so here are just 2 spectra that you can easily tell which product you get out. This anti-Markovnikov product has a methylene group, a CH, the rest of the cyclohexane ring. You have a more complex spectrum, a lot of different types of H's, non-equivalent H's, that'll come up at different chemical shifts, and also different splitting patterns. The CH2 next to the O will come up here between 3 and 4. You'll have this OH hydrogen split by the CH2s, giving you a triplet, which you can't, I haven't blown that up, but you can see that. And just a bunch of different saturated H's here. If you got the Markovnikov product, you would have had this methyl group not split by anything, so you would see a singlet, a little past 1. And here are relative areas, but basically you would end up seeing this was integrating eventually to 3 to the rest of the H's here. Okay, let's move into C13 NMR. We haven't dug deep in this. C13, the reason why it's carbon 13, that's a naturally occurring carbon isotope that does have a nuclear spin. So that works with NMR, it's NMR active, but its abundance is really low. Most of the carbon on Earth is C12. So only about 1% is C13, even far less is C14. But what we can do is still utilize it in NMR, but we have to use what's called a Fourier transform. And basically, you take a ton, hundreds or thousands of individual NMR spectrum and average them out. Let me show you the difference this makes. Without that effect, you get a really noisy NMR spectrum for the carbon 13 NMR. But if you could do the Fourier transform and average those out, you get a much cleaner spectrum showing the key peaks here. Okay, so just to let you know, you're only going to see singlets here. We're not going to see any of the sort of splitting patterns that you observe with the proton NMR. Number one, you have a low abundance of the C13, and there's a decoupling method used that does not allow for coupling with hydrogen. What you guys need to be able to do is just read a carbon-13 spectra that goes from 0 to about 220 and know where the peaks reside on here, the types of peaks. In this more downfield region, 160 to 220, that's where you'll have your carbonyl carbon signal come up. This is huge for you because if you're given just spectral data or even a formula, knowing whether or not you have a carbonyl group in there will really greatly help you figure out the structure. You can also confirm that with IR. Most of those carbonyl shifts go in the 1700 wave number region. This region here will indicate to you you have aromatic carbons or just alkene carbons. Nitriles will come up here too. Further down, not down, but more upfield, is the alkyne. And then this region here, there's a lot of overlap. But if you suspect you have a CO, either with the ether, an alcohol CO, or an ester off of a carbonyl group, you better be looking for something in this range here, 60 to 80 usually. And then more of your saturated H's are going to be upfield in the 20 range. Okay. Very similar to proton NMR, some general factors that determine chemical shifts. These include electronegativity. The more electronegative the atom nearby, the more downfield it'll be, more to the left. Pi systems, circulation of pi systems where the electrons are running in a current, such as in aromatic rings. These can cause de-shielding, which is why you do see those aromatic carbons further down, and just absorption of sp3, sp2 carbons. Those will show up in those specified regions. Okay, let's just take a look. Let's analyze two compounds. This is 2-butanone here, and the first thing I look for is there a carbonyl or not? Do you have something like 180 on? You do. You have a peak. It went off the scale, so they put it up here at 208.7. You have a carbonyl. What about the other guys? You should have 3 other distinct carbons, and good, you see 3 other peaks. The one closest to the carbonyl will come up next. So this one here, the C3, will show up a little before 40, and then your methyl group next to the carbonyl will show up a little more upfield from that. And then finally, just your primary methyl group here coming up a little before 10. Okay, let's contrast that with the spectrum for parabromoacetophenone. Look at what you have. You have a benzene ring, you have a carbonyl carbon, and you have a methyl group off of that. So again, carbonyl carbon, that's going to be way downfield between 180 and usually 200. You do see that. Your aromatic should be in this 120 to 140 range. How many peaks should you see? How many different carbons do you see? The benzene ring has 6 carbons, but there's some symmetry. So this first one next to the carbonyl is one distinct carbon. But the 2 carbons after that, 4 and 4 prime, those are equivalent. The next carbons, 5 and 5 prime, those are another set. So 6 is also different. So you should have 1, 2, 3, 4 different peaks in this aromatic range, which you do. And you'll see greater signals for the 4, 4 prime and 5, 5 prime. The methyl group, as you would expect, is closer to 20. Okay, so let's practice. You guys assign the peaks. Here we have an ester. This is methylpropionate. So you guys just analyze the spectra, assign which peaks are going to get 1, 2, 3, 4. So hopefully you picked, and you guys can pause this and check back in, but hopefully you picked carbon 2 as this, way out here, closer to 180. Look at this, you have a CO bond. So that carbon here, carbon 1, is next to a very electronegative element. So that should come up here in the 50 range. Then the one next to the carbonyl, that methylene, so that carbon here, C3, should be next, a little past 20. And then your methyl group next to just a normal CH2 is going to be closer to 10. So I just wrote that out here if you want to double check that. Okay, the last thing I want to discuss is something called DEPT, carbon-13 NMR spectroscopy. This is a special type of way to run a carbon-13 NMR spectra. And the reason you do it is basically you have a lot of different carbons you're having trouble assigning. It's going to help you identify which ones are CH carbons, which ones are methyls, which ones are CH2s. So if you run a DEPT experiment, what you do is you run 3 different types of experiments. The first one will generate a normal C13 spectrum. The second will generate a spectrum. This is a depth 90. It'll only show CH carbons. So this is a nice way to just pick out, okay, out of my whole big spectrum, which ones only have CHs. Then you could run a depth 135. The spectrum will show methyl and CH as positive signals, but it'll show methylene, CH2, as negative. So this is very useful to pick out different peaks that correspond to these different types of carbons. Let me give you an example. And this is our last bit for the video. We're going to look at this alcohol here that has a double bond in it. So I have 2 vinylic carbons that should show up in that 120 to 140 range here. I don't know which one is which yet. Maybe I could guess. Then I have this, something 60 to 70. Which carbon could that be? And then I have a bunch here. Okay, so the way that you do this is you first, again, get the full spectrum. Then you can run the depth 90. That will only tell you which ones have CHs. So the 2 peaks show the CHs. That means this guy has a CH, that's one of the vinylic. This one has a CH, this one does not. It has 2 methyls attached. So clearly this peak out of the 2 vinylics are this one to the right. That means this peak here is this guy. Next, the only other CH one is this carbon attached to the OH, which is what we suspected for a group here in that 60 to 70 range. Okay, the third spectrum is from the depth 135, so it's still going to show those 2 CHs, but the other positive peaks are the methyls. So you could pick out the methyls, these 2 and this. And then the other 2 showing negative signals are CH2s. So then you can pick out those. These are the CH2 ones. All right. So that's where I'm going to end here. You guys have a lot of practice. You guys can do the practice worksheets. There's homework for you. And eventually there will be some practice exam for this section of the final. All right.